large deformation diffeomorphic algorithms out there right now. So diffeomorphism is defined as it's a geometric entity that has differentiable every point is differentiable, and it's also inversely differentiable. I don't know what that exactly means, but the way I understand it is, the way I explain it to my middle school your daughter is, it's something like a silly putty. You know, you can bend and manipulate as you can, but you cannot tear or fold. So it's very flexible thing. You can bend, but you have to preserve the geography, the topology. And these three algorithms, Dartel in SPM and FNIRD in FSL and symmetric normalization in ANTS, they all use diffeomorphisms for their to implement large deformation normalization scheme. Dan, did you have a question?
No, I think Sully kind of covered it.
Oh. And the reason why we are using symmetric normalization is not because Penn folks developed it, but it outperforms other nonlinear normalization algorithms. So Arnold Klein conducted very ambitious normalization algorithm evaluation study in 2009, and the left axis is the ROIs, and the x-axis is the different algorithms, and it shows ranking. And to make a long story short, the bluer, that algorithm is better. So this blue column represents symmetric normalization, and the last column represents Dartel, SPM Dartel, and this one is SPM unified segmentation, and this one is FNIRD. And this one is something called ART, which is as good as symmetric normalization, but I couldn't find it where I couldn't find how to get it. So that tells us, you know, which one to use. So going back to Marna's question, a bonus of good registration is that we can do registration-based quantification of volume change, because registration has got so good. So if we use the deformation information out of that registration, then we can automatically quantify the volume change amount, volume expansion or volume reduction. So this technique is called tensor-based morphometry or deformation-based morphometry, and more people use the name deformation-based morphometry because tensor means, you know, nothing. It means just you know, an array of numbers, but you know, what does that mean? Array of numbers. So deformation is the amount of, you know, transformation. So that sounds much better. So Okay. So let's say this is original brain, and this is template brain. This is actually smiley, but this grid is actually deformation, something called deformation field. You can say, and it numerically it is expressed this way. And based on this deformation vector field, we can construct Jacobian matrix for each point. And the determinant of that Jacobian matrix, if you remember the formula that you learned in your linear algebra course, then the determinant of Jacobian matrix encodes Voxel's volume change. So this is Jacobian determinant map. So for each point, we can get Jacobian matrix, and out of that Jacobian matrix we get Jacobian determinant value, and this is the map of it. And the brighter it means you have to expand that area, and the darker you have to contract that area. So, or vice versa. It's not critical. So anyway, so it has this volume change information in the Jacobian map, and it is in the template space. So if we align all the Jacobian map, then we can actually statistically test, where in the brain in a group of patients had the most atrophy. So that's a good thing. And Jacobian determinant is not as threatening as it sounds, because conceptually it's very very intuitive. So if Jacobian determinant is 1, so for example, on this left eye, you don't have to warp at all this left eye to make it smile and wink. So so the Jacobian value is 1, which means there was no volume change. But for the left eye, Jacobian value is 1/3, which means it had to expand 3 times, and Jacobian value is so this particular point, like the end of the mouth, Jacobian value is 3, which had to shrink 3 times. So it's so if it's more than 1, then it has to shrink, and it's less than 1, it has to expand. And to make the values more normal, you sometimes take natural log and then make it follow normal distribution. So the distribution at the end ranges from minus something to plus something, and it follows nice normal distribution. So you will hear in the deformation morphometry papers, you will hear a lot about log Jacobian, but you don't have to be, threatened. It's, it's this. So this is an example. We use this technique to quantify TBI patient's brain, and we first built a custom-based template, A is control subject's template, control subject's average. So and B is patient's average. You see this enlarged ventricle. This is template based on patient, and then we average these two to get unbiased template, custom template, and then we work individual brains, which is D, to this template, custom template C, and then we get this deformation field E, and as a result we get Jacobian map G, and the result of applying that deformation field E is normalized brain F. So this original brain looks like this after the normalization. And this is the result of the quantification of atrophy. So this is based on something like 20-something subjects, and blue color means volume expansion, and red color means volume reduction. So in fine matter structures and thalamus, there were volume reduction and ventricles volume expansion, and you can correlate these with behavior just like as you do in your VLSM based on focal lesion. But so far I talked about how to deal with diffuse injury, but we have also this focal injury in our population. On right, there's a case where there are bilateral frontal focal lesion, which is pretty large, and the problem with this is that if we run large deformation normalization scheme on this, then this lesion completely goes away because the working is so powerful and not regularized, if you say. So that's the issue, and one way of dealing with that problem was called cost function masking that was originally developed by Matthew Brett in 2001, and in this method, so at that time he ran SPM2 nonlinear normalization, and he still got this distorted images. So if you run just nonlinear normalization on this lesion brain A, then with focal lesion right there, then you have this severe distortion around lesion area. So what he came up with was you mask this focal lesion area with a mask, and then you exclude this area when you calculate cost function. And cost function is a metric that measures the similarity between the two images. So in this case, the template and your individual image. So more specifically, he used SPM2. So in SPM2, the cost function is sum of squared difference over the whole brain. So when you calculate that, you exclude